Hi everyone. So this is Balakrishnan 20BZ1035 and I'm here to talk about the topic that is the mining the block. This is a part of my blockchain digital assignment 2. So let's start. So what is mining all about? Okay. So if you take mining, right, like mining in blockchain is nothing but solving a complex mathematical problem. Okay. So in order to get a gist of what it is all about, just go back and look into the mining of gold in the gold mines. Okay. In which you need a lot of machineries, manpower, etc. etc. So in a similar way, in blockchain, in order to mine a block, right? In order to add a block into the blockchain network, you need to do a lot of computation. And that is nothing but solving a mathematical problem, basically, on the whole. Okay. So it is all about mining. So now let's see the steps. Okay. This is a bird's eye view. Okay. So this is what the overall thing that happens in the blockchain. Okay. So if you start, right, if you just go with the start. So in the start, like we will receive the transactions, then we will validate all the transactions that are valid in the block. We group them together and put it in a block. We use Merkle tree for all those things. Okay, so now let's go to the next. Then we will create a block header. So what does the block header contain? The block header contains the hash of the previous block, then the current block's transaction, then the timestamp, then the nonce value. Okay, nonce value is nothing but it's a parameter. Okay, it's a value. Okay, so I'll tell you more about it, like why we require nonce and why, etc. etc. Because we cannot change any of these things, whereas we can change nonce. By this, the overall hash of the block can be changed. Okay, so that is the idea. So now, then what we'll do means we'll hash the block header. Okay, and then we will see whether the resulting hash value is less than the target or not. Okay, target range or not. That is what we will check in the fifth step. And then if suppose we have got the correct hash value means, then we will proceed to the next step, or else we will repeat the step by changing the nonce value. As I told you, we can change the nonce value and then again try 3, 4, 5, and then you will be coming back here. So if suppose you have found it correctly, right, if your resultant hash value is less than the target value means, target hash value means, then we will receive a reward in the form of reward, or else, and then transaction fees, etc. etc. will be receiving, and then we will be updating our own blockchain copy, and then we will also broadcast that particular copy into the network. So now, so this is what happens, and this entire process again and again repeats, and this is how the blockchain network is being created. Blocks, a lot of blocks chained together in the network. So now this is the pictorial representation. The transaction is initiated, it is being broadcasted, and mining takes place, and then it adds. This is the all good scenario. Okay, this is the all good scenario. So now let us go into the technical deep dive explanation of what mining is all about. Okay, so now if you take in the simplest terms, right, so mining is nothing but hashing the block's header repeatedly again and again until the resultant hash matches to a specific target value. So just see this, right? So this is how hashing works. We all know already. So I assume that everybody knows how hashing works and the properties of the hashing, etc. etc. So let's see. Okay, suppose we are having an input, no matter what the size of the input is, when we give it to the SHA-256 algorithm, right, it will give an output that is of fixed length, that is of 256 bit. Okay, so now this 256 bit, right, what we do means we are here now restricting this output. We are telling that this output should be within this range, less than the target value. Okay, we generally what we do means we will prefix the leading bits by zeros, and we will say less than this we need. Okay, so by this we are controlling this, right? We are controlling this particular output. Okay, we are telling this is what I need. So in order to get that output, we will manipulate the input. In that we manipulate the nonce value, and then we will get it. So this is how we will do it repeatedly again and again and we will find. So one of the important properties to note here is that we cannot see any pattern, or we cannot judge what is going. We cannot predict, okay, what the output is going to be of the hash value. Okay, so this is one of the best property of the hash value, which gives us the proof of work, the property itself to the blockchain. Okay, so if you see this, right, like we will be changing the nonce value again and again, and we will be trying to achieve the resultant hash value, the desired hash value. Okay. So now the proof of work algorithm. Let's see how the proof of work algorithm works with an example. Okay. So in this example, if you take this is like this is the phrase. This is a string. Okay, I am Satoshi Nakamoto. If you give this particular phrase to a SHA-256 algorithm, you will get this hash. Okay. So this is a hash which is in hexadecimal, and this is of 256 bit. Okay. So now this is the script. Okay, this is a script. Okay, this is a Python script. What we are doing is that we are like iterating. Okay, from 0 to 90. Okay, and then this particular value, right, we are always adding with this text. Okay, and then we are generating. We are giving the overall appended text to the SHA-256 algorithm, and then we are calculating the hash of it. Okay, 256 bit algorithm, and we are calculating the hash of it. So in order to understand the analogy, just think that this text is of the this text is nothing but the block's header. Okay, this text is nothing but the block's header. That has been, this is that block's header, and this has been the transactions, all those things. This cannot be changed. The point is this cannot be changed. Whereas this value which we are appending, right, this can be changed. Okay, so that is why we are calling it as nonce here. So this is the thing. So this is the output of that particular script. If you see this very carefully, right? So when I appended 0, different hash. When I appended 1, different hash. When I appended 2, different hash. Like that, it will be keep on going. Okay, 2 observations here. No matter how many times you give this particular value to the 256 SHA-256, right? You will be always getting this hash. Okay, no matter how many times you run. Okay, so that is the point. Okay, for the same input, you'll be getting the same output. For different input, you'll be getting different hash value. So that is the point. So here another one more observation to note is that here if you see for 13, right, you are getting a leading 0. Okay, so this is what? This is how you'll be running like different random nonce value, and then we will be getting the desired target value. Okay, so now that we can see the points to look. Okay, here the number which is used as a variable is the nonce. Okay. So the block's headers, other parameters like timestamp, transaction values, Merkle trees, header, head, all these things are unchangeable, whereas nonce is changeable. Okay. So and then if you see this, right, like if you see this, I'm Satoshi Nakamoto 13, this resulted in a leading 0. Okay, that means if suppose we have set 1 bit as 0, right? So this is our target value 0xx 00000. This is our target means. Then this is the valid hash value. Okay. So but it took us 13 iterations. So this is how the proof of works comes in. We need to do this much of work in order to achieve this hash, not to find this hash, right? So now setting the target. If you are going to set the target like this, right? So this is the threshold target. Okay. This is a threshold target. Okay. So generally, if we decrease the target, then finding the hash becomes more and more difficult. Okay, if the target is lesser, finding the hash is more difficult because more number of computations need to be done in order to find a value, hash value that is lesser than the target. Okay, so now you might not understand this that easily because it's not that intuitive. So let us go to an analogy. Okay, let us go to a dice analogy and then understand this. Okay, so we all have played dice games, right? So if you roll 2 dice, right, there are a lot of possibilities, right? You can get 1-1, 2-2, 1-2, like that till 6-6. There are 36 combos in total. Okay, so say I'm keeping the target of 12 and I'm telling you, you need to roll the dice such that you're getting a value that is less than 12. Okay, so what are the possibilities that can lead you to less than 12 is that 1-1, 1-2, like that, everything except 6-6, because 6 is will lead you to the target of 12, which is not less than 12. So there are 35 combos. Okay, say the target is 3 now. Okay, then there is only one combo, 1,1, which is equal to 2, which is less than 3. All other combos will be fetching you a value of 3 or more than 3. Right. So this is more difficult to get than this. Okay, this is more difficult to achieve than this. So the similar way, the target that is lesser is very difficult to achieve. The target which is greater is easier to achieve. So this is a result observation. So lower the target, less range of values, higher the difficulty as more number of hash computations is required. Higher the target, more number of values, lower the difficulty, and less number of hash computations is required. So we can control the difficulty and the time taken to produce a block in the network by adjusting the target. So this is the point. This is a very important point to understand. So now if you come here, right, here also it took us 13 hash computations to find the nonce that worked. Okay, we gone through like 1, 2, 3, 4 like that 13 iterations in order to find the perfect hash value, that is 13. Okay, so this successful result is also the proof of work, because we have done this amount of work in order to find the correct nonce value, and it takes only one iteration in order to find whether this hash is working or not. Because if I give you this string and if I tell 13 is the nonce which I have found, you can easily take these two, append it together, give it to SHA-256, and then find out whether the resulting hash is less than the target hash or not, right? So now in real-time blockchain network, the Bitcoin's proof of work is very similar to the above problem. Okay, so in real time also the same thing happens. Okay, miners construct a candidate block filled with transaction. Next, the miner calculates the hash of the block header and see if it is smaller than the current target or not. If not, then the miner will modify the nonce, usually incremented by once, and then try again. So exactly whatever we saw in the Python script is going to happen to the block header in the blockchain network. Okay, so at the current difficulty in the Bitcoin network, miners have to do quadrillion times of iterations in order to find the correct nonce value. Okay, so this is the simplified proof of work implementation, which you can see over here. So this is the proof of work implementation, right? We have simplified it and then a Python script. Okay, so what it is doing, we can see in the output. Okay, so what we are trying to do is that for this particular difficulty, for this particular number of bits, what is the there's nothing but difficulty is 2 power 3, which is 8, 2 power 4, 16, 2 power 5, which is 32. Okay, so when the number of bits of leading zeros are being restricted, right, the difficulty increases and the time taken is increased. That is what we are going to see here. Okay, when it is 3 bits, right, it took us 9 nonce, okay, 9 iterations to find the correct nonce, which is 9, and it took us 0.004 seconds. This is the hashing power. This is the hashing power. So the speed at which our computer finds the hash. This means for 1 second we can calculate 25,000 hashes. Okay, similar way for everything it is that. For 3, 4, 5 bits, all the bits it is that. Okay, so the important observation here is that for 3 bits it is 9 nonce value and 0.004 seconds. For 4 bits it is 25 hashes and it is 0.005 seconds. For 5 bits it is 36 nonce value and 0.006 seconds. And the hashing power is somewhat changed as per our requirement. Okay, so now for 22 bits, right, this is the nonce value, which is very huge. It's going in millions, right? It's going in millions. And 13 seconds, it takes 13 seconds. For 23 bits, it is 110 seconds, which is a galloping difference, right? Like from 13 seconds, it came to 110. And then it's 195 seconds for 24 bits. Okay, so now if you go to 26 bits, right, it took us 84 million nonce values. Okay, so many iterations it took, and it takes us 665 seconds. Okay, which is almost like 10 minutes, right? So it's a lot of time. Okay, so you can see this result observation, right? So even if you increase the difficulty by 1 bit, right, there is an exponential increase in the total time it takes, right? So that can be seen over here, right? Like for 24 bits, it's 195 seconds. For 26 bits, it's 665 seconds. This is very high, right? So the entire 256 bit number space, right? If you're going to constrain 1 bit to 0, that is one leading bit, if I constrain it to 0, the search space reduces by half. Okay, are you getting that? So by this way, we are like, if we constrain more number of bits, we are like reducing the search space by half. Okay, divided by 2, divided by 2, divided by 2, like that we are restricting the search space. Okay, so in 26 bits, it took us 84 million hash atoms to produce a hash that has 26 leading bits as 0 with a speed of 120,000 hashes per second. Okay, and it takes us 10 minutes on a consumer grade laptop. Okay, so try to understand. Okay, the more number of bits you're restricting as leading zeros, it is becoming more and more difficult, and it takes a lot of hash attempts, and which indeed increases the time. Okay, which indeed increases the time. Okay, to compute, to find the correct nonce value. So why is this? Now one question will come to our mind. Okay, why is this difficulty adjustable, and who adjusts it, and how is this being done? Okay, in bitcoins, every block is generated for one block is generated for every 10 minutes. Okay, on an average. Okay, so to keep the block generation for always like 10 minutes, the difficulty has to be adjusted, right? Because as the time evolves, there are more computers coming into the market which are like more powerful, and if we pool the computers together, we can easily find the blocks in a more faster, right? If you pool a lot of computations, right, a lot of CPUs together, we can find it so easily, so faster, right? So that is why we have kept that difficulty as a dynamic parameter that can be changed. Okay, our end time is that for one block it should take 10 minutes. Okay, in order to hold that, we will adjust the difficulty, either increase the difficulty or decrease the difficulty. Okay, so how it is being done, let us see that. Okay, so after 2016 blocks are being added, right, the ideal time, okay, after every 2016 blocks, we will always check the network and we will always adjust the difficulty. Okay, so the ideal time is what? 10 minutes into 2016, which is 20,160 minutes, right? So this is the equation. Okay, just note this equation very nicely. New difficulty is equal to old difficulty into actual time it takes divided by the ideal time it takes. Okay, so if suppose it has taken more time, right, if the actual time is more than 20160, then we have to reduce the difficulty in order to reduce the overall time it takes to the ideal 10 minutes. Okay, if suppose it takes lesser time, right, then we have to increase the difficulty. Okay, so that more number of hash the nonce iterations are like increased now, and then it takes more time. Okay, so that we can increase the time to the ideal one, that is the 10 minutes. And this is a decentralized process again. Okay, so by this way we adjust the difficulty, we increase or decrease it so that the number of hash attempts increase or decrease. More difficulty, more hash attempts, more time. Less difficulty, less hash attempts, less time. Okay, by that way we will make sure that every block is being generated for one block is generated for every 10 minutes. Okay, so the block generation time for one block is 10 minutes. We will make sure this is constant. Okay, so at last, okay, what happens is the validation process. Okay, so the validation process is the last process, right? So this is an independent process. Okay, so this is how we will make sure there is no double spending happens or any other fraudulent activity is not happening, is being controlled by the independent validation. Okay, so there is a series of tests which has been done in order to validate a block, and then only it has been propagated to its peers. Okay, so if you see this, right, the miner has to construct a perfect block, okay, based on the shared rules. Okay, in order to find a correct solution for the proof of work algorithm. Okay, if they don't do it right, if the miner has cheated, right, then he will not receive the block reward, he will not receive the transaction fees, and all the money is wasted in the electricity and all other costs. So by this way we have kept a checkmate, okay, for the fraudulent people who are in the network. Okay, so this is how, okay, this is how it happens. And this independent validation is the key component of the decentralized consensus. So that's it. Thank you very much for listening. Bye.